Welcome to another class of analysis of Boolean functions, and today we continue with lecture 3. We continue to discuss the topics in chapter 3 of Ryan O'Donnell's book. Okay, so let me share my screen here. Okay. Okay, so let's start with, so in this lecture, we will explore a little bit some of the things about learning functions, learning like how algorithms can learn Boolean functions. Okay, so okay, so usually we have like, let's see, be some subclass of functions from the Hamming cube to plus or minus 1, so Boolean functions. Okay, so you have a certain family of functions. So this could be, say, like symmetric functions, or it could be like monotone functions, or it could be, I don't know, functions with a certain special property, something like that. And you want to come up with a learning algorithm. So we want to come up with some learning algorithm for this class of functions. And algorithms can be like of two types generically. Say it could be learning from random examples. Or it could be learning from queries. That is, I can request access to x and f of x, say, for all x in the Hamming cube. While in the first, say, in the first, the only thing I would like to know is like I get a random examples of entries f, x, and answers f of x. Okay, and in this class, I will be focusing on the first guy, and I will leave as a reading exercise to learn about the second type of learning algorithm. Okay, so definition. So we say then an algorithm A learns C with error epsilon. So it could be one of the two types, say, but with an error epsilon, and probability, say, greater or equal than 1 minus delta, where delta is some small number, if for every f in the class, you use that as input in your algorithm A, and you get as output a function h with a distance of h to f less or equal than epsilon, and that holds with probability. Um, greater or equal than 1 minus delta. Okay, so that would mean the following. So I have an algorithm that I get a function in the class. For each function in the class and output, I can apply a certain procedure of, say, either access to those values to every single those values, or just by random examples, say, and then I come up with some function h, and that h is pretty close to your guy f, and this happens with some probability. Say the probability that your output h satisfies this is greater or equal than 1 minus delta. So it's a large probability. Okay. So the question here, one of the questions is given C, how efficient A is in learning C. Okay, so you have an algorithm for learning C, how efficient I can learn this class C. Okay. Okay, so we will see that there are some classes that you can learn in polynomial time. So the goal here is to answer that question is polynomial time. Okay. Yep. So great. So let's see first. So for proving some of the results, I will need some lemmas. So let me state the first proposition that I would like to show. Proposition 1. So say given access to random examples, there is an algorithm A, which takes as input say some subset of n, some delta greater than 0, and some epsilon, say between 0.5, and outputs some f tilde of s, such that and the running time is this time. Okay. So for the question here is, I give you some f, and I would like to know, oh, sorry, this is supposed to be catchy. And I would like to know how can I approximate the Fourier coefficients of f, okay? And this is saying that I can approximate it just by, say, random examples. I just know a bunch of these samples, and I can come up with a good approximation that works, say, 90% of the time, or like 99% of the time. And how long the algorithm will take to produce that approximation, well, it would take this amount of time. So if you want that it works, I say 99.99% of the time, then you have a big number here, so it would take longer. But in any case, it's polynomially in n, and for most applications, you only need like 90% of the time is fine, and so it's polynomially in n and 1/epsilon. Okay, which is always nice. It doesn't take exponential time to compute such approximations. Okay, so to prove this lemma, we will need some basic results in probability. And so let me state here. So lemma 2 is, so let, say, zi from I equals 1 to m be independent random variables, and assume they are real valued, such that, say, a is less or equal than zi, less or equal than b for every I, and suppose they all have the same expectation. Okay. Then let z be the average of these guys. Then we have the following inequality. So this is one of these tail bounds, which are usually useful in mathematics when you're dealing with probability distributions. And this is sort of a Chernoff type bound. There are also other names here. Also can be called like Hofdinger's inequality. I don't know how to pronounce this name. Hofdinger's inequality. I won't say who was the actually author of this thing. It's one of these variants, but it's a, you can see it as a Chernoff right here. Sort of a Chernoff type bound. Okay, so let me prove that. Okay, so this is controlling the tail of this expansion away from this average, from its own mean. Okay, and well, the first of all, you can assume that mu is 0. That's trivial. And also, this is less or equal than the probability of z greater or equal than t. plus the probability of minus z be greater or equal than t. And this is just because if this is true, then either z is positive or negative. If it's positive, then this is true. If it's negative, then this is true. And so by the union bound, we can bound by this. So that's where these two comes from. So we just need to deal with one of these probabilities. And what is this? So you apply the old trick of this exponentiating everything, and then you take s to be some parameter to be chosen later, and you just apply Markov's inequality here. This is Markov inequality, which is one of these trivial inequalities that we all know. And then, well, you use the factor independent to write this as a product. ZI, okay. And now I'm going to apply here what's called Hoeffding's inequality, which I will prove in a moment, which says that each one of these terms in this product is bounded by the same quantity, which is this guy here. I believe it's minus. Yes. And then we have m of these terms. So I have to raise to the power m. And so in the end, we get this. Okay, and then now you choose s that minimizes the right-hand side, and the s that minimizes it is this guy. And so you get that probability of equal to t is less or equal than, if you just replace everything, this will be 4t squared over m divided by b minus a squared. And this guy would be what? This would be 16t squared m squared. Yes, b minus a squared divided by b minus a to the power 4 times 8. Oh no, there was a mistake here. This guy was actually, yeah, this guy here is actually a plus, sorry. This guy here is actually a plus. Yeah, this thing doesn't make any sense, actually, if it was a minus. This thing is actually a plus. Yes, this thing is actually a plus, sorry. This is Hoeffding's inequality. And so this is actually a plus. Okay, then now we can, well, this guy cancels with this. Just got a 2 here. There was a m that I forgot downstairs here, which then also cancels with that guy here. And so the conclusion that these two terms cancel, and you just get the 2 there, and everything goes away. Okay, and that would finish the proof. Okay, that's what we wanted to show. And then this 2 comes from the fact that we have these 2 factors. Because you can replicate the proof for this guy, of course. Okay, so what is that inequality? Let me show that inequality. So that inequality is that we use, if you notice, what we used was the following. Say this was a lambda, this was some zi, say a fixed z1 because it will be the same for every I. And then we use that this thing is less or equal than e to lambda squared b minus a squared divided by 8. And we use here for lambda equals s over m. Okay. And we're assuming here that the expectation of z1 is 0. So we know that a is less or equal than 0, less or equal than b, because a is a bound for below for z1 and b is a bound above from z1. So, and 0 is the average. So we need to have that. So this is what we're doing. Okay, so we want to prove that. And so what you do is you use the fact that this function here is convex. So you're going to use the fact that the exponential is convex to write this as this is just an identity, and then use the fact that this thing is convex. Okay, and so if I take expectation of this side equals expectation of this, which is equal expectation of that, but then this will be equal to, well, the expectation of z1 is 0, so this is just and now a is negative, so it can substitute everything by this. Okay. And then I would leave as an exercise to show that this is indeed less or equal than e to 1 over 8 lambda squared b plus moduli of a squared. Okay. And that's exactly the lemma we wanted to show, because in this guy it was positive, so this would be plus moduli, etc. Okay. So that finishes the proof. So, okay, so we have this lemma, and I want to show this proposition. So now let me show this proposition. Okay, so what's the proposition? Let's read it again. So I'm given access to these random examples, and I'm saying just for a fixed function f is fixed here, and I want to create an algorithm that can learn that function from random samples, and that gives me a good estimate for the Fourier coefficient that works that works with high probability, saying that for any delta is small, I have probability 1 minus delta. Okay, and the running time is only polynomial in epsilon and n. Okay. Okay, so what I can do is say I have one y1, y2, ym, which are IID, random variables, and all uniformly distributed in the Hamming cube, Hn. And what I can do is I can learn yj f of yj. Because these are random examples, then I try to learn those guys. Okay, so say I have a dice with a 2 to the n faces, and I flip that guy, and that there shows up a vector of plus and minus ones, and that's the vector that I go ahead and measure this. So I go ahead and compute this value, then I flip the dice again, and I get another guy. This will give me another vector. This will be a y2, and then go ahead and measure that again. And so I know that f hat of s is what? Is the expectation of x to the s fx, okay, if x is uniformly distributed in the Hamming cube. But what I can do is I can compare that. Is that close to, say, just doing this average? Okay, and I could define this as f tilde of s. Okay, so I would like to know what's the probability of 1 over m being greater or equal than epsilon. Okay, and I would like to know when this is less or equal than delta. That's the question. Okay, but now I can see if so this is now a random variable. Okay, because I put several random variables here. So what's the average of this? Well, since they're independent, it will be just the average of this guy, and the average of this guy is this guy. So what I'm doing here is just a sum of independent random variables. You're doing the average, and I'm removing here the average of that sum, the expectation of that sum. So this is exactly as we did in the lemma. So this is by applying the lemma. I guess was the lemma 2. Was that lemma 2? Yes, lemma 2. So you can apply lemma 2 to this, and this will be what? Less or equal than twice the expectation of minus this supposed to be, so let me look at the, so it's supposed to be like 2 epsilon squared, the number of variables I'm using, which is m dividing by the bounds. So 2t squared, oh, not t, epsilon. M, is that it? Yes. And then I have to divide by the values that these random variables can attain, but f has only plus or minus 1 as value. These are Boolean functions. If I forgot to say that, then I should say. So this guy is Boolean. Okay. So this thing can only vary between plus or minus 1 as well. So this thing at the bottom is going to be what? Plus 1 minus 1 squared, which is 2 squared, which is 4. So this is going to be just that. Okay. And I want to know, and this is less or equal than delta. Well, this is exactly if and only if m is greater or equal than log of 1 over delta divided by epsilon squared. times some constant, say. So let me take the log. If we divide, it will be 2 over delta. Yeah, if delta is sufficiently small, it's just be a constant, okay? So I could take, bottom line, I could take m to be O of that, of this size. Okay, so if I take just m random samples of more or less this size, I can make a good approximation for the Fourier coefficients just by doing very naive things. And what's the computational time here? Well, I have to do m things, m valuations. Every single of these valuations, these random variables here are vectors actually of size n. So it's m times n and computations. And we have also this epsilon square here. So just roughly bounding everything by above, obviously, the total time would be something like polynomial in n 1 over epsilon times log of 1 over delta. And that finishes the proof. Okay. So just by standard bounds in probability theory, you can come up with such an algorithm. But this proposition is telling you something very nice, which is the following theorem. So this is telling you something very nice, because this is telling you that, well, if I have an algorithm that can learn the Fourier coefficients of a class of functions. So this was for a specific function. But if I have a class of functions and I can learn that the Fourier coefficients of any function in this class in polynomial time, then just by expanding some more time, which is also polynomially, I can actually construct a good approximation for f. And the good approximation will come just from these coefficients f tilde. Okay. And this is the extent of this theorem. So let C be a class, and suppose that A is learning via the randomized examples so suppose that there is A such that for every f in C, A learns f via these examples and outputs a collection f of subsets of n on which the spectrum of f is epsilon concentrated. And let me just recall what that means. That means that the sum of the Fourier coefficients of S is squared for S not in the family is less or equal than epsilon. Okay. Then using additional polynomial time, we can modify A, so to produce some, let's say, A tilde, such that A tilde outputs some function H with the distance H to F less or equal than epsilon with probability greater or equal than 1 minus delta. Okay, so that's exactly what I said. So if you have some class and you have an algorithm that can learn that class somehow, you don't know how yet, somehow, and produce a set. So for every function to produce a set, a collection of sets whose the spectrum of the function is concentrated in that set F, that is the sum on the complement is small, then you can actually produce a function H that is close to it. So recall that for Boolean functions, I wrote this at some place. Yes, so this guy here, it's the distance. For Boolean functions, this is equal to this, which is also equal to 1/4 of minus HL2 squared. Okay, so the distance here, well, I should say exactly what this is. So this is by definition the probability that H is not F, which for Boolean functions is equal to that. Okay. So it bounds the probability of H being different. So it's some H which is pretty close to F, and it produces that H with probability. I mean, this inequality holds with probability 1 minus delta. Or you can also think as it produces an H which satisfies that with probability 1 minus delta. It's the same thing. Oh, proof. Okay. So what you can do is this for each so what do we have? We have some F in the class, and the algorithm produces this family F of subsets. So for each S in this family, what do? We apply proposition 1 to find F tilde of S, an approximation for the Fourier coefficients that works, and I will use these parameters with probability greater or equal than 1 minus delta of the size of the set. Okay. And so this happens in time, which is Pauli by proposition 1. the size of this guy, because, well, the epsilon is being divided by this, and so that's why it enters in the polynomial time, n times log of 1 over delta. Okay, so for each f, I use the algorithm, and then for that, let's say I concatenate the algorithm with proposition 1, and I produce these approximations f tilde. Okay. And so, so for each member of this class, so what's the probability then that for all s belonging to f, I should say something first. In time for each s. Yeah, so recall that probability is a proposition 1. Go back. Yeah. I should emphasize here that for each s, there is an algorithm, but because of course this algorithm, the selection of the y's depend on the s, because by the proof we used those random variables here, and then for different s's would be different random variables that would be in the sum, so it would be different choices. So the algorithm will choose a sample, examples, random examples. It will differ from different different sets S. Okay. So I give an f in this class, and I produce a family, and then for each s, I have this, and then so that's why I divided by these numbers, because now, well, the family is finite, and so therefore I can say what's the probability that for every s in f I have this. Okay, or by the union bound, that's less than the sum of the probabilities, but each one is less or equal than what? Each one is less or equal than delta divided by the cardinality. So this would be less or equal than the cardinality. So this is union bound, which is the probability of the union of events is less or equal than the sum of the probability of these events. That's the union bound. So this is delta. Okay, so you know that the probability that oh, sorry, not this. Not every, there exists. The probability that there exists an f that violates what we want is less or equal than the sum of the probabilities, not. So then this is union bound, and this is delta, okay? So that means that with probability greater or equal than 1 minus delta, all these inequalities here are satisfied for every s in the family. Okay. Okay, so then f tilde. So then I conclude that the soup of s in this family is less or equal than this with probability greater or equal than 1 minus delta. And that's the conclusion. Okay. So now how, so okay, so I have my initial algorithm A, which given an f produce something, a family of sets, and then from these family of sets, subsets, I get each guy in this family of subsets, I create an approximation f tilde, and so then now I have an approximation f tilde that works for every member in that family, and now I can define my function h, which would be the sine of the sum in all these family of sets. And that should be close to f of x somehow. Okay, so let's try to measure the distance of h to f. Okay, so the sign could be 0. I mean, this guy could be 0 at some point, and you define it to be plus or minus 1, whatever. You choose, you normalize your sign function so that it only produces plus or minus 1. That means you have to choose what you want for sine of 0. Say you choose 1, but you can choose also minus 1. Okay, so now so h is a Boolean function now, precisely defined. Okay, so what's the probability that f is not h? Well, that's the same as the expectation of the indicator function of f being different than saying the sine of g, and say that this function here, internal function here, is the function g. Okay. But this is less or equal than the expectation of f minus g squared. Because, well, if f is plus 1, and so this is plus 1, and the sign is different, so this is negative. So then you do plus 1 minus something. So this is bigger than 1, which is bigger than this value. And if this is minus 1 and this is positive, so this would be negative, and this you're subtracting something. So this would be less than minus 1. So the square would be bigger than 1, again, bigger than this value. So then you have this inequality pointwise, and so for the expectation of one is less or equal to the expectation of the other. But this, again, is just the L2 norm. So this would be just this, say if it's in the family, and plus if it's not in the family, then we don't have f tilde, we just have g. Oh, sorry, is the other way around. This is f hat. If it's on the family, is tilde, and if it's not on the family, it's just f hat. And now what is this? Well, by construction, you know that this is less or equal than the number of members in the family. Each one of these terms is less than epsilon times the cardinality of the members in the family by the inequalities we have. And this other side, well, we know that's less or equal than epsilon because the algorithm A outputs some guy with epsilon concentrated. So by assumption, this thing was less or equal than epsilon. So this thing was 2 epsilon, okay? So I have to maybe put a 2 here in the statement of the theorem. So we can, so then we produce that. And so this holds with probability greater or equal than 1 minus delta. Okay. So so again, you see if the algorithm, so and now this thing has its own, because the algorithm A can output f with certain, say, high probability because it's randomized. I didn't say here how high the probability was. So I could say 1 minus delta. Again, so then it would be 1 minus 2 delta in the end. So maybe I should say here, well, the A, suppose that there is A such that for every f, A learns f by randomizes and outputs a collection to be set into spectrum. It is. So an output, say here, with probability greater or equal than 1 minus delta, say. Then with additional poly time of this, one can modify such that with probability, say here, 1 minus 2 delta. Okay, Why? Because, well, we just produced something with probability greater or equal than 1 minus delta, but in the final inequality, this bound here coming from this works for probability greater or equal than 1 minus delta, and this bound here works for probability greater than equal to 1 minus delta. So in the end, I get that the distance of h to f is less or equal than 2 epsilon with probability greater or equal than 1 minus 2 delta. Okay, because you have to put all the two algorithms there together, and so that finishes the proof. So what this is saying, that if I have a randomized algorithm that can learn Fourier coefficients, I can learn where the Fourier coefficients of a function is concentrated, then I can come up with a good approximation just by spending some extra polynomial time. So the whole business of learning a class can now be reduced to learning where the function is concentrated. Okay. Okay, so one of the classes you can learn is this one, for instance. If the class of functions are concentrated up to degree d, then we can learn that by random examples and time this, because, well, you know already, you don't have to use any algorithm. You already know that your function is born with Fourier coefficients concentrated up to degree k, say. And so for each one of these sets, I can come up with a good approximation of the Fourier coefficient of S, and then I can just, and so what's the time to actually create a good approximation by the proposition, by the theorem we just showed? Well, you just apply proposition 1 to learn it, and it will be in time poly the size of the class and 1 over epsilon, and you multiply by a log of 1 over delta if you want probability 1 over delta. But what's the size of f? Well, the size of f is the number of sets of size at most k. So the size of f should be this of 0 and j, and this is O of n to the power k. So that's why you get n to the power k there. Another class you can learn is, for instance, the class of functions which have influence less or equal than t, and we can learn again by randomized examples with error less or equal than epsilon in time poly what? Nt over epsilon, 1 over epsilon, which is O of n over t over epsilon. So again, if you fix t is again polynomial time, and this is simply because we have that inequality that every function f is epsilon concentrated. So recall that we proved that every function f is epsilon concentrated up to degree I over t over epsilon, I over f. So, and this is less or equal than t over epsilon. So this is the degree, and that's what we're using here. It's all you can use the previous observation. Okay, another class you can learn fast is also the class which have say this, which has noise stability is small, and this is just because we can learn in also poly n1 over delta time, and then you can learn this because you have this inequality which we showed. And then again, you can use the result, the first observation to learn that in that time. And to finish, I just want to mention some of the, so this I learned because I have theorem 3, and actually in theorem 3 we didn't use an anytime randomized example, so I can actually, so suppose you have an algorithm that's random or not, we don't care, they can actually output a set where f is concentrated, then you can then learn that class fast just using an additional time. So so you can think of, okay, and then using these theorems, we have these examples that I mentioned here. But then we also have the Goldreich-Levin algorithm. So that would come up as the initial oracle algorithm A that we had. And so how can we actually come up with an algorithm that tells you where f is concentrated, or the Fourier coefficients of f is concentrated? That's the Goldreich-Levin algorithm that I'll leave as a reading exercise. And in there, you can actually learn where f is concentrated. So for every parameter tau, you want to know the sets exactly, the sets where f is big, say where the Fourier coefficients are bigger than tau, and you know that these are exactly the sets in this family, and all the sets in this family have size at least greater than tau over 2. So there is an algorithm to actually come up with this set of Fourier coefficients for f, and then it works in time n over polytime n and 1 over tau, this parameter. And this is one of these divide and conquer algorithms. So I would leave as a reading exercise, but basically what you have is you split your Fourier coefficients in 2 buckets, and you select the bucket which has the largest weight, and then you split it again, and so on, and so on. Okay, sorry. So and so on, and you keep doing that until you come up with these sets. And using that theorem and the previous theorem we showed, we can prove, for instance, theorem 4, which I will also leave it as an exercise. So if you have a class that you know that for every function in that class, the Fourier spectrum of f is epsilon concentrated in at most m sets. Okay, so you have the upper bound for the number of sets where the Fourier transform is concentrated. And so therefore you can use the Goldreich-Levin algorithm to actually come up with a list of those sets. And then we can use the previous proposition by randomized extra time. You can do an extra randomized algorithm to actually produce good approximations for f hat, and then produce a good approximation for f. Okay, so we can actually prove this. So this is one of the exercises in the book as well. So I'll leave that as an exercise. And that's pretty much what I prepared for this class. And I hope you enjoy it, and see you next class.